So, hello everyone. My name is Emmanuel, and I'm going to talk about SkinnerDB. Traditional database management systems typically make very strong assumptions about queries and data when generating query plans. If those assumptions hold, great, then we get an optimal query plan. But if those assumptions don't hold, then we don't have any guarantees anymore. Our goal with SkinnerDB was to create a system which sits at the other end of that spectrum and does not, essentially not make any assumptions about the query or the data, and still tries to give at least probabilistic guarantees on how the expected execution time relates to the optimal execution time for a given query. More precisely, we focus on join ordering decisions because that is what has most performance impact in practice, and we use reinforcement learning in order to learn those join orders, because those reinforcement learning methods give us guarantees on making near optimal expected decisions even under uncertainty. Now, there has been a lot of recent interest in using machine learning for query optimization, but SkinnerDB differs from other recent work as follows. We don't learn from past queries for optimizing future queries, but instead we learn during the execution of the current query in order to optimize the remaining execution of the current query. In that way, we avoid generalization problems because everything we learn is immediately relevant and applicable to the current query. In order to enable that, we divide query execution into micro-episodes. Each micro-episode just takes a few tenths of microseconds, and in each episode, we first select a join order, then we execute that join order for a fixed number of steps, we measure the evaluation progress that we made during that time, and we learn from that to select better join orders in the following episodes. And at the same time, while we are doing this, we are generating result fragments by executing those join orders. We collect those result fragments and we stitch them together until we have obtained a complete query result. And at that point, we return the result and we terminate the process. Now, the first question is, what learning framework can we apply in such a context? Now, the natural framework here is reinforcement learning, where we generally assume that we have an agent which takes actions in an environment, and from those actions result rewards. The goal of the agent is to maximize the accumulated reward, but initially the agent doesn't know which actions will lead to high rewards. So the agent faces a choice between being greedy and trying actions that have worked quite well in the past, or being curious and trying actions about which we know very little. This is called the dilemma between exploitation, trying things which have worked well, and exploration, which means trying new things. And research in the area of reinforcement learning has resulted in learning strategies that optimally balance between those two motivations in order to guarantee near optimal expected rewards over time. Now, applied to our specific scenario of join order learning, the agent is, of course, the system SkinnerDB. Taking actions means selecting join orders and trying them for an episode. The environment is characterized by query and data properties, and rewards corresponds to evaluation progress. Again, we can either try join orders which have looked promising so far, or we can try new join orders, and if we balance optimally between those two, we can get near optimal expected reward, which translates into near optimal expected evaluation progress. More precisely, we use an algorithm called the UCT algorithm from the area of reinforcement learning, and that algorithm represents the search space as a tree. Here you see a small example. Each path from the root of that search tree to one of the leaf nodes corresponds to a join order. And the UCT algorithm associates those tree nodes with statistics that allow us to calculate confidence bounds on the quality of the join orders that are located in specific subtrees. And the UCT algorithm considers specifically the upper bounds of those quality confidence bounds. So it is, in a sense, optimistic and always selects the child with maximum upper reward estimate. So here we first select table R, then we look at the statistics for those child nodes, and here we continue with S and then T. So that is the join order we select. Of course, this tree gets pretty large for larger queries, so we want to avoid generating all of that tree at once. Instead, we start with a very small tree, and then we just grow this tree into the direction of join orders that currently seem promising. This is how we learn. But in order to make this efficient, we have some very specific requirements on the execution engine. Because first of all, we want to get some first meaningful impression about the quality of a join order by executing it just for a few steps. And second, we want to switch between different join orders with a very high frequency, so the execution engine has to allow the switching with very low overhead. And finally, as we switch between different join orders, so we suspend and resume execution for one join order repeatedly, it means that we want to associate join orders with execution state such that we avoid doing redundant work. But since we are trying thousands of join orders for a query, we also need to keep that execution state as small as possible, because otherwise we have prohibitive space consumption. Standard query optimization essentially fails according to all of those criteria. Let's assume that we want to join those four tables from the left to the right-hand side using, for instance, hash joins. So we would first consider scan the first table, then we would join it with the second table, then we would start joining it with the third table, but now the current episode ends, so we have to suspend execution. And at this point, we have learned precisely how long the first join takes, but we have not learned anything about how long the remaining joins will take. And that means we cannot make any reliable assumptions about the overall quality of this join order, so we fail to get meaningful early quality feedback. Also, if we execute those joins as usual, then we might generate a large intermediate result after the first join already. And once we switch to a different join order, we can, of course, discard that intermediate result. But if we do this, then we have to redo the work later if we use the same join order again. So by doing that, we create essentially switching overheads. On the other side, what we can do is that we keep the intermediate results, but if we do this for all the join orders that we're experimenting with, then ultimately we'll have prohibitive space consumption. Now in the following, I propose a better strategy which essentially corresponds to a very extreme form of pipelining. We start by selecting one first tuple in the leftmost table. Then we advance to the second table in our current join order, and we select the first tuple in that table which satisfies all applicable join conditions with the currently selected tuple in the first table. And of course, we can use an index structure in order to find that tuple in the second table efficiently. After that, we advance further to the third table and select the first tuple that satisfies all applicable join conditions with the currently selected tuples in the first two tables. And we do pretty much the same thing with the final table. And if we find the first matching tuple in the final table, it means that we essentially consider a tuple combination that corresponds to one result tuple in a join result. So we can add this result fragment to our overall result. And we search for more satisfying tuple in the final table until we have found all of them. Then we go back to the third table and we select the next matching tuple in that table, and now we assume that the current episode ends. A first observation about this depth-first strategy. If I want to suspend the execution of this join order and resume it later again, the only thing that I need to remember is the currently selected tuples in each of those tables. So I just need to store one record ID at most for each of those tables. So the execution state that I need to associate with join orders is actually very small. Also, if I switch from one join order to another one, the only thing I need to do is to store, to back up the positions of the selected tuples for the current join order. And then I load the last selected tuples for the new join order, and I just set my counters accordingly. So also the switching is a very low overhead operation. And finally, in terms of quality estimates, if I execute things in this way, then I can calculate a reward metric that correlates quite well with evaluation progress. Now, in the simplest case, I can just look at progress in the leftmost table during the current episode. So I look at the tuple at which I start my episode, and I look at the tuple at which the episode ends. And then I evaluate progress by how many tuples I have advanced my pointers, and setting this in relation to the total number of tuples that I have in the leftmost table. So here we have advanced by 2 out of 5 tuples, so that corresponds to 40%. Now, this is proportional or correlated with execution progress because, as you can imagine, each possible join order terminates after it has reached an evaluation progress of 100% according to that metric. However, faster join orders will divide those 100% over a smaller number of episodes, so their average reward per episode will be higher. And that means that faster join orders will indeed be assigned to a higher average reward by this principle. Of course, here, this is simplistic because we only consider one of the tables. In our actual system, we use a more sophisticated metric that considers progress in all tables, and in the paper, you find a detailed description of that metric as well. But already with the simple metric, we can somehow get early quality estimates, of course not the precise quality, but some unbiased estimator. And furthermore, since we have that faster join orders are associated with higher average rewards, and since the UCT algorithm obtains near optimal expected rewards, we can conclude that our evaluation speed, our expected evaluation speed, is also near optimal if we have enough input data to process. So far we have talked about join ordering, and that is indeed the most complex component of SkinnerDB, but we also have a pre-processing and a post-processing phase. In pre-processing, we generate, for instance, indexes that are used to speed up join order processing. In the post-processing phase, we do grouping, aggregation, and sorting. And here, I can only outline parts of our technical contribution. In the paper, you find more fine-grained reward metrics. You find several methods to share progress between different join orders, which is very important for good performance. And we also implemented join order learning on top of standard execution engines, where we force the original database to execute specific join orders on data batches. If you do this, you need a different algorithm. You have to have a look into the paper for more details. Now, in our experiments, we evaluate SkinnerDB against a variety of baselines. SkinnerDB is implemented in Java. It's specialized for in-memory processing, and it has a column store architecture. Now, before experimenting, we were unclear about how our system would perform against traditional database management system. I mean, we clearly have going for ourselves that we very reliably converge to good join orders, but we also pay for that with learning overheads, with join order switching overheads, and with some amount of redundant work. So it's not clear which of those factors will dominate the comparison. Here you see some first results for the join order benchmark we compare against 2 baselines in the slides, but you find many more baselines in the paper. Here it is Postgres and MongoDB. I distinguish between single-threaded and multi-threaded evaluation because our current implementation is mostly sequential and cannot benefit too much from parallelism because our join phase is currently sequential. And indeed, for single-threaded processing, we beat those traditional database systems. For multi-threaded processing, we were slightly slower than MongoDB when it comes to the SkinnerDB version that we experimented with for the paper. We are currently re-implementing the approach more efficiently, and the new implementation is actually a little bit faster again. Now, those plots here tell the story behind those performance comparisons. Here, on the right-hand side, you see that our per-tuple processing overheads are significantly higher than for the baselines, and that is due to learning overheads and switching. On the other side, however, we see that we generate significantly less intermediate result tuples than the baseline. You see this on the left-hand side, and that is due to the fact that we select better join orders and more reliably. And so we see that by trading execution efficiency for more reliable join ordering, we actually make a pretty good deal performance-wise. Also, if we break down results by single queries, here we calculate which percentage of execution time different systems spend with the k most expensive queries, where k is on the x-axis. You see that SkinnerDB distributes execution time much more evenly across different queries, so you get a relatively robust performance. And if we compare the performance impact of different features, we see indeed, as expected, that join order learning is the thing that makes SkinnerDB fast. Now, if we compare against guaranteed optimal join orders, we see that SkinnerDB actually comes very close to the performance of the optimal order, also when executing those orders in different systems. On the other side, the join orders proposed by SkinnerDB work often much better than the orders of the original optimizer. So one use case is also to use SkinnerDB to find optimal join orders to execute in different systems. Now, in the paper, you see many more results. Our sweet spot are, of course, queries with user-defined functions, because for us, that doesn't really make a difference whether it's a user-defined function or a standard predicate. You find comparisons against different baselines in the paper, and we also evaluate our approach on top of existing database management systems, which has mixed result on the join order benchmark due to increased overheads by using the standard execution engine, but in more extreme cases, it can actually help as well. In the paper, you see more experimental results, but already based on this extract, we have seen that even though we don't use any data statistics, no cardinality model, and no cost model, we learn near optimal join orders from scratch via reinforcement learning. We can already receive some interesting performance trade-offs. If you want to have a quick look at a very early prototype version of our new SkinnerDB implementation, you can do it here. Thank you very much for your attention, and now I look forward to your questions.
Any questions? Right there on the back. Carlo.
Thank you so much. This is fantastic work. I think
Thank you.
I can say the most interesting thing I heard at SIGMOD'.
Thanks.
I would like to see this, your thoughts on applying this in the context of sort of big data systems, because your use of no statistic, no assumptions, kind of weak assumptions, it is great for databases, but we're pretty good at getting statistics there. In big data, there is no way. The data shows up, you need to process it, and then you never touch it again. So what are your thoughts about applying this in that context?
Well, I mean, I have to say it depends on the context. A priori, having larger amounts of input data can even be beneficial for our system, because it will give us more opportunity to learn a good join order on the fly. So here, every learning we do only happens within the current query execution. So even if you have a fresh data set and you only run one single query on top of it, then this approach is already applicable. And at least in terms of formal guarantees, we actually get better bounds if the input data is larger. One problem with big data would be that our current approach is sequential in the join phase, but we are actually currently working on an extension to make this parallel. So I feel that the resulting approach might actually be applicable quite well even to large data sets.
Sorry, quick follow-up. Parallel is great, but distributed is harder than parallel, right? So how do you maintain this state and switch across if you have 1,000 parallel machines that are collaborating in computing the join?
That is a great point. So right now we are focusing on in-memory, like on multi-threading, and the advantage of that is that the different threads can quite easily exchange information about optimal join orders with relatively low penalty. You're absolutely right that if you have a distributed system and communication is difficult, then that might make things harder because one node might find a very interesting join order, but telling the other nodes might take some time. So I agree, there is challenges there, but that's also one scenario that I would like to consider in the future.
Thanks.
Unfortunately, okay, one more question. We are anyway running into lunch, so let's take the time for it. Right over there, please. Carsten.
So thanks again for the talk. So I was wondering, your join algorithm, so compared with traditional hash join, seems very inefficient because it jumps from one table to the other, needs to do a lot of index lookup somewhere in the table. So do you have an idea if you would know the optimal plan and do a traditional, let's say, more efficient join algorithm, so how far away are you, or how much overhead do you have compared to that optimal execution strategy?
Well, we compare against the optimal execution plans calculated according to the C-out cost matrix, so we minimize the sum of intermediate result sizes. From what I understood, you refer to the fact that we jump back and forth between different tables. That would be a larger disadvantage, I would say, if we do on-disk processing. So this is focused on in-memory processing, which means that the overheads for random access become somewhat less pronounced than with disk scenarios. In a way, we are using hash tables in order to do those joins efficiently, right?
Unfortunately, we are running out of time.
So during
Let's take it
pre-processing, we
offline.
create the hash tables, and during runtime, we just use it.
Let's
All
take
right.
it offline. Let's thank our speaker again.